Okay, so picking back up with evaluating limits analytically. So we discussed in the last video the different properties of limits. So now we're going to look at some limits that we can evaluate using direct substitution. So just plugging in whatever value x is approaching into the function that you're taking the limit of. And when you're using direct substitution, you can also think about it from the perspective that you're applying these different properties of limits. So like the limit in A of this quadratic x squared minus 2x plus 4 as x approaches 3, we know that polynomial functions, quadratics, are smooth continuous functions. So whatever the function is approaching as x approaches 3 will be the same thing as the function evaluated at 3. Remember that first case of when the limit exists. So we can just actually plug in 3 for all the places that x is and then simplify. But we can also think about it as applying that addition, subtraction property of limits, right? And taking the limit of each term of this polynomial. But using direct substitution, we'll just plug in the 3. So is that 9 minus 6 plus 4, which is 7. So that limit is equal to positive 7. Now we're going to take the limit of a rational function as x approaches 1. Again, we could think about from a property of limits perspective, taking the limit of the numerator, which is a cubic polynomial, as well as the limit of the denominator, which is a linear polynomial. So from that perspective, you can just think about evaluating each of those. We're allowed to plug 1 in. So we would have 1 cubed minus 9 divided by 1 plus 1 would be negative 8 divided by 2, which is negative 4. Okay, so that limit is negative 4. Now for the square root of 8 minus x squared, you can think about applying the power property for limits, since that square root is the same thing as the 1/2 power, and then taking the limit of 8 minus x squared, or just thinking direct substitution, which is allowed because of these properties. We would have the square root of 8 minus negative 2 squared. So that would be the square root of 4, which is 2. And then the limit of tangent as x approaches pi over 4, well, tangent of pi over 4 would be equal to 1. Tangent of pi over 4 is positive 1. And then the last one on this page, x times cosine of x as x approaches pi. The limit of x times cosine of x as x approaches pi would be pi times cosine of pi. Cosine of pi is negative 1. So that would be pi times negative 1, which is negative pi. Now we always want to try direct substitution first for evaluating limits. But sometimes direct substitution doesn't work. Now, piecewise functions, you do want to be careful, especially if what x is approaching is where the domain of the different pieces of the piecewise changes. In that case, you probably want to think about one-sided limits, where you would try direct substitution with the one-sided limits, but you just want to be careful anytime you're dealing with a piecewise. But for other types of functions, direct substitution is going to be your first strategy for evaluating the limit. So if direct substitution doesn't work at first, because specifically you run into this issue of you get 0 over 0, That might be because there's what we call a removable discontinuity. And in section 1.4, we're going to talk more about different types of discontinuity. But for now, we can just call it a hole, which you guys are familiar with. At x equals to c, when you're taking the limit as x approaches c of f of x. Now, 0 over 0 is an indeterminate form. There are different indeterminate forms, like infinity over infinity is an indeterminate form. 0 over 0 is an indeterminate form, which means the limit might exist or it might not when we run into this indeterminate form. But there's a factor that's causing that 0 over 0. So causing the numerator and the denominator to both be 0. And when you run into the indeterminate form as x is approaching c, it means that the factor that's causing the 0 over 0 is x minus c. And you need to try and get rid of that factor using algebra in order to see if the limit actually does exist or not. Because remember, if it represents a whole, which it doesn't always represent a whole, we're going to look at some where that's not actually the case, but most of the time when you run into 0 over 0, it means it's because of a whole. And then we've seen that when there is a whole, the limit can still exist. It's just the function is undefined at that specific x value. So let's look at these two different limits and talk about them. So first of all, if we try direct substitution, so plugging 2 in to this first limit, well, 2 squared is 4, so 4 minus 4 would be 0. Plug in 2 for x in the denominator. We would run into 0 over 0. Don't say the limit is equal to 0 over 0. That's not something that we can say. That's not something you would write on a free response. If you want to make a little note to yourself that you run into 0 over 0, just like I did for when you try direct substitution, that's fine. But you're not actually saying the limit is equal to 0. So this is a rational function. And because when we plug in 2, we get 0 over 0. We know that that common factor that we're trying to get to cancel is x minus 2. So the numerator factors to x minus 2, x plus 2. And when you're rewriting the function that you're taking the limit for, make sure that you're still using the limit notation until you actually try direct substitution again. You need to have that limit notation. So at this point, I can see that x minus 2 and x minus 2 will cancel, leaving me with the limit as x approaches 2 of x plus 2. So now we can try direct substitution again. We plug in 2 for x, and we get 4. So for thinking about what is happening graphically at x equals to 2, in this case, it's a hole. So this graph has a hole at x equals to 2. And we know that because this is our original equation. It simplifies to be x plus 2. So the graph of x squared minus 4 over x minus 2 would look like the line x plus 2, y equals to x plus 2, so a line with a slope of positive 1 and a y-intercept of 2, but it would be undefined at x equals to 2. There would be a hole at x equals to 2. But the function would still, as x is approaching 2, the function would be approaching what we would want to fill in that point with, which would be the point 2 comma 4. So it would be approaching the function value of 4. So we can say there's a hole. Graphically, you guys know from pre-calc, there's a hole at x equals to 2. Now let's look at this other limit. So again, if we plug into, this is a different function. If we plug into, it's still rational. We get 0 over 0 again. And I've already factored the denominator here. So we can see right away that we can simplify by canceling an x minus 2 in the numerator with one of the x minus 2 factors in the denominator, and that leaves us with 1 over x minus 2. Now when we try direct substitution, notice that we end up with 1 over 0. And 1 over 0, well, that would mean the function is undefined. But you guys know from your pre-calc knowledge that when we simplify this equation and we still have the domain restriction of 2, that actually represents a vertical asymptote. And if there's a vertical asymptote at x equals to 2, that means that the limit can't exist, or is DNE, does not exist. Now, you would have to do further investigation using one-sided limits to see whether or not you could say positive or negative infinity, since you guys are familiar with the parent function 1 over x, and this graph will look like the simplified version of the equation. So that's 1 over x shifted to the right 2. As x approaches 2 from the left and the right, they would approach different infinities. So really this limit, we can only say DNE. We're going to talk more about when we run into this situation in section 1.5. But relying on your pre-calc knowledge, we know graphically this function would have a vertical asymptote at x equals to 2. And then from our knowledge from section 1.2, we know that this limit would not exist. It's just DNE. Okay. So we're going to look at some common methods, algebraic methods, for when you run into the 0 over 0 case. So some methods which I have fun names for. I can't take credit for the fun names. I heard them somewhere else. But some common algebraic methods that you can fall back on or try whenever you do run into the 0 over 0. Remember, try or think about mentally trying direct substitution first and then try one of these algebraic methods. Okay, so the first one is FODO, which means factor and divide out. So this would be usually for like a rational function. So when you try direct substitution, you get 0 over 0. Now, it's super helpful if you know, so you know that by the factor theorem, when you plug in whatever C is in and you get 0 over 0, you know what that common factor is. So that can be really helpful with the factoring part. So limit as x approaches 1 of x cubed minus 1 over x minus 1. You can see you would end up running into that 0 over 0 case. So we know that x minus 1 is that common factor that needs to be eradicated. It would be helpful for you guys to remember difference of cubes. So this is x minus 1 times x squared. It would be plus x, right? So plus, because the x times 1, and then plus 1. Over x minus 1. That x minus 1 factor cancels in the numerator and denominator, so that leaves us with the limit as x approaches 1 of x squared plus x plus 1. So now we try direct substitution, and that's 1 squared plus 1 will give us 3. So that limit is 3. Okay, if we plug in -2 here, what would that be? That would be 12 minus 10 minus 2 would be 0, and then over 0. So we run into indeterminate form. You don't have to make that notation. I'm just doing it kind of as a reminder that we did think about direct substitution first. Okay, so limit as x approaches -2, factoring the numerator, 3x times, we know x plus 2 is that common factor that's going to divide out. So to get that will have to be a -1 to get -2 as the constant there. So it's helpful with us, it's helpful for us for factoring to know that x minus whatever c is a factor, the common factor. Okay, so then those x plus 2's will cancel. That leaves us with the limit as x approaches -2 of 3x minus 1. Notice I am not dropping the limit notation until I try direct substitution again. So we get -7 for our limit. Okay, the next method that you can try for if you run into the 0 over 0 is what I call RATCON. So short for rationalization conjugation. So you're going to try and rationalize either the numerator or denominator of a fractional expression by multiplying by a version of 1, which that version of 1 would be the conjugate of either the numerator or denominator, whatever needs to be rationalized in order to have that factor eradicated that's causing the 0 over 0. So like this first example here, notice if we thought about direct substitution, we get 0 over 0. So x is the common factor. We can't see the x in the numerator, but we can use algebra in order to try and get that x out of the numerator. So I'm going to try multiplying by the version of 1, which is the conjugate of the numerator. So the square root of x plus 1 over itself. Okay, so still limit as x approaches 0. So simplifying that numerator, notice that when we multiply by the conjugate, that's like a difference of 2 squares factored. So thinking a squared minus b squared, this would be x plus 1 in the numerator minus 1, right? A squared minus b squared when it's multiplied out. And then in the denominator, the x is still there, and then times the quantity x plus 1 plus, of the square root of x plus 1 plus 1. Make sure you have the parentheses. Okay, so simplifying the numerator, notice that the 1's here will cancel. So now this x can cancel with this x. So that was what was causing the 0 over 0. So we'll have the limit as x approaches 0 of 1 over, 1's all that's left in the numerator, the square root of x plus 1 plus 1. Super common mistake here to just write that simplified version as the square root of x plus 1 plus 1. But remember, that's in the denominator. So all that we're left with, even though everything cancels, all we're left with is 1 in the numerator. Okay, so now we can try direct substitution. When we do that, and I'll show it for you here, but you guys don't, it's okay if you want to go directly to saying, oh, that's 1/2. Okay, one more example of RATCON. So if we were to try direct substitution, we'd get 0 over 0. You can do the mental check. Let me actually multiply just so I'm not rewriting the limit all over again. It's okay if you want to show here. It's like we're multiplying inside the limit here, right? We're multiplying this function, the expression that represents the function, by a version of 1. So that'll be the square root of x plus 2 plus root 5, which is the conjugate of the denominator here. So that's the limit as x approaches 3 of, I'm going to leave that x minus 3 factored out because I know that that's what I'm trying to get to cancel. So times the square root of x plus 2 plus root 5 over the denominator will end up multiplying it because that's a difference of 2 squares when it's multiplied out. So that'll be x plus 2 minus 5. So I can see x minus 3 will cancel with the denominator, which is x minus 3. That leaves us with the limit as x approaches 3 of the square root of x plus 2 plus root 5. And then trying direct substitution again. That's 2 root 5. Okay, LCM over LCM. So it's the least common multiple of, this is whenever you're dealing with complex fractions, you're going to multiply by a version of 1, which is the least common multiple of the denominators of the complex fractions that are involved. So we want to get rid of those complex fractions to see if we can eradicate what's causing the 0 over 0. So in this first example, when we plug in 0, we'd get 1/2 minus 1/2 in the numerator and 0 in the denominator. So, okay, just like before, I'm going to multiply by my version of 1 now, just so I'm not rewriting the limit over and over again. So the least common multiple of those denominators would be 2 times x plus 2. And I'm going to leave those factored, so that'll be easier to think about distributing. So when we're distributing, okay, so we're distributing this product to this fraction. And when we do that, that would leave us with the x plus 2's canceling and leave us with 2. And then we think about distributing to the minus 1/2. So the 2's will cancel. And that'll leave us with minus, and make sure you have your parentheses here because it's subtracting the 1/2. So it'll be minus x plus 2, the quantity x plus 2. And then in the denominator, I'm going to leave that in factored form. And we need to think about distributing that negative in the numerator. So that'll be 2 minus x minus 2 over 2x times x, the quantity x plus 2. So now looking at what will cancel, 2's cancel. This x can cancel with an x in the denominator. We do still have this minus. So the numerator will be left with negative 1. And the denominator has 2 times the quantity x plus 2. So then when we plug in for direct substitution, that ends up being negative 1/4. Okay, similar example, but now our complex fractions are in the denominator. If we think about trying direct substitution, we get 0 over 0. So the version of 1 that I'm going to multiply by, looking at the denominators here, I have a 6 and an x minus 6. So to get those to cancel, I'm going to need to multiply by 6 times x minus 6 over itself. Okay, so limit as x approaches 0 of the numerator will be 6x times the quantity x minus 6. And then thinking about distributing, and I'm going to walk you through this in the denominator because students tend to struggle. It can be helpful also to put like brackets or some sort of grouping symbol around the big numerator and the big denominator, just to remind you to distribute correctly. So distributing to the 1/6, the 6's will cancel. I'll be left with x minus 6. And then when we distribute to 1 over x minus 6, the x minus 6's will cancel and we'll be left with 6. And I can just put plus 6 here because it is plus. So then looking at what will cancel, the 6's cancel, this x can cancel with x in the denominator. So we end up just being left with the limit as x approaches 0 of x of 6 times x minus 6. So that'll end up being, when we plug in the 0 for direct substitution, that would be negative 36. All right, sledgehammer. Sledgehammer is if you have no other options. You've exhausted all of your algebra options for simplifying, but you run into this 0 over 0 case. Okay, so 0 over 0 if we try direct substitution here, and that's thinking about plugging 0 in for h, right? Because that'd be x squared minus x squared. So it would be 0 over 0. So sledgehammer is just brute force. I'm going to multiply everything out and see what cancels. It's that h that in the denominator that's causing the 0 over 0. So I need to get an h in the numerator to cancel with the h in the denominator. So multiplying out x plus h squared, that's x squared plus 2xh plus h squared. And then the minus x squared is there. And then looking at what will cancel, x squareds cancel. Notice that with the terms I'm left with, I can factor an h out. So now the h in the denominator will cancel with that h in the numerator. And then when we try direct substitution, again, I'm plugging 0 in for h. So it would be 2x plus 0, which is just 2x. And this is kind of looking ahead. We'll talk more about like what this is in chapter 2. Okay, this one's same idea. If you thought about plugging 0 in for h, you'd get 0 over 0. So I don't see one of the other methods to use that would get the h out of the numerator in order to have it cancel with that h in the denominator. So brute force, sledgehammer, limit as h approaches 0, multiply everything out and simplify. So x squared plus 2xh plus h squared. Distribute the negative 2, so that's minus 2x minus 2h plus 1. And then distributing the negative, that would be minus x squared plus 2x minus 1 all over h. Gosh, that's yucky. All right, let's look at what cancels. X squareds cancel. This is the best part. 1's cancel. 2x's cancel. Notice each term that we're left with has an h that we can factor out. So factoring that h out. Okay, now those h's can cancel. Oops, here's some pink. So trying direct substitution, that would be 2x plus 0 when we plug the 0 in for h minus 2, which is 2x minus 2. Again, looking ahead a little bit. Okay, so these previous examples, when we ran into 0 over 0 and our limit still existed, it was because there was a hole at whatever it was x was approaching. We're going to look at a new parent function, which I don't know the technical name of what you would consider this parent function to be. It's a type of step function, and it's very similar to what we call the sine function, but it has a slightly different domain. But it's a type of step function. You'll see what I mean in a second. So we're going to rewrite this equation as a piecewise defined function, but by thinking about the graph. Okay. So for thinking about the graph, here's my x-axis, here's my y-axis. I'll be 1, -1. Okay, so if we were to plug in 0, we would get 0 over 0, that indeterminate form. So this equation is undefined at 0. But what happens at 0? Is it a whole? No. If we were to think about plugging any value less than 0 in for x, so -1/2, -1, -10, notice that the absolute value of that negative value would be positive. And then when you divide it by the negative value, that ratio would be -1 for all values of x strictly less than 1. So the way that we could draw that graphically, there's no point at x equals to 0 there, but for every value directly to the left of 0, the output, the y-coordinate, would be -1. And then for x strictly greater than 0, that ratio would be +1. So the graph ends up looking like this. And if you think about, so these two expressions have the same outputs. And if you thought about the alternative definition of absolute value, the square root of x squared, you could derive that relationship. And the fact that they're equal to each other. So I'm going to write this equation as a piecewise. So y equals to absolute value of x over x, which is the same as x over the absolute value of x. Right? All of these statements have the same y values, the same domain and range. So output is -1 when x is strictly less than 0 and +1 when x is strictly greater than 0. Now, let's evaluate these limits. So as x approaches 0 from the left of absolute value of x over x, that one-sided limit would be -1. As x approaches 0 from the right, it would be +1, which means that the two-sided limit is D/E. Because those one-sided limits don't agree, because the one-sided limits are not equal to each other, all we can say is D/E. So there's not a hole at x equals to 0. There's a jump, which is why I'm calling this the Jumpman function, because for whatever reason, I picture the Michael Jordan logo whenever I think of this function. I don't know. So I'm calling it the Jumpman function. Maybe it'll help you remember. But remember, we want to think direct substitution for limits. So like when we think of taking the limit as x approaches 2, if we plug in absolute value of 2 is 2 divided by 2, that would just be +1. Okay? So we're going to use our knowledge of this parent function in order to help us evaluate some more complicated Jumpman-like functions. So some where there's maybe just some transformations and translations happening, and then some that are even more complicated, but we can use our knowledge of this parent function to help us with evaluating the limit. Okay, so thinking about taking the limit as x approaches 5 from the left of this function, so absolute value of 2x minus 10 over x minus 5. Well, the GCF of those two terms that are in the absolute value bars is 2. And if I rewrote this, where in the numerator I pulled that 2 outside of the absolute value, that's not changing anything about the outputs, right? because no matter what, the numerator would have positive outputs. Pulling that 2 out, it's not going to change anything. If you're multiplying by a positive 2, you're already multiplying by it. Okay. So now I'm going to think about applying, and I wish I had put more room so that I could have vertical steps here. That would be better, but I don't, so it's okay. I'm going to think about applying some properties of limits here. That scalar multiple rule, I'm going to pull the 2 out. So I have 2 times the limit as x approaches 5 from the left of absolute value of x minus 5 over x minus 5. So when I think about, okay, well, what is that minus 5 doing to the graph of absolute value of x over x, right? Like we can think of that as the parent function. That minus 5 is a horizontal shift to the right 5. The 2 is a vertical stretch by 2. So we could think about that without pulling the 2 out. But I'm gonna think about applying the limit property, because there's an explanation where you can think about that vertical stretch and like what's happening. But I'm gonna think about it as from the limit perspective. So I pulled that 2 out because that's a property of limits. I'm allowed to do that. So now thinking about absolute value of x minus 5 over x minus 5, that's absolute value of x over x shifted to the right 5 units. The limit as x approaches 5 from the left, so that's this graph just shifted to the right 5 units. So that jump is now happening at x equals to 5. So as x approaches 5 from the left, that limit, that function would be approaching -1, right? You could even think about plugging values in to the left of 5. So if you plugged in 4, here, you would get -1. So this is equal to 2 times -1, which is -2. Okay, so let's look at same function that we're taking the limit of, but as x approaches 5 from the right. So we can do the same thing where we can pull that 2 out. And again, horizontal shift right 5, but approaching 5 from the right, that's going to be +1. Or you could think about plugging a value to the right of 5, so like 6 in for x. When you do that, you get +1. So this is 2 times +1, which is just 2. Now those one-sided limits both exist, but they do not match. They are not equal to each other. So all we can say about the two-sided limit would be dne. All right, getting a little more complicated. So first thing, I have a ratio here, right? A fraction. I see the absolute value bars in the numerator. So I'm like, wait, is this a Jumpman kind of function? This x squared that's hanging out here, that's not part of Jumpman, but that's okay, because we have these properties of limits that we can fall back on, right? So I could always think about rewriting this as the limit as x approaches -3 from the left of x squared, and then times the limit as x approaches -3 from the left of the absolute value of 2x plus 6. Now, 2x plus 6, 4x plus 12, they don't match each other, but what if I factored out the GCF of 2 from the numerator and the GCF of 4 from the denominator? So if I do that, I'll write this in a couple steps. So I'll have 2 I can pull out of the absolute value bars, absolute value of x plus 3, divided by pulling the 4 out times x plus 3, okay? So I can also apply that scalar multiple rule again, and I could pull out a 1/2 from that limit, or I could even put the 1/2 with the x squared. So now I have the limit as x approaches -3 from the left of x squared, and I'm going to pull that 1/2 out. Limit as x approaches -3 from the left of absolute value of x plus 3 divided by x plus 3. I can use direct substitution for the x squared, so that would just be -3 squared, and then times 1/2, and then times, so thinking about this limit, x approaches -3 from the left. That plus 3 is a horizontal shift to the left 3. So -3 is going to be where the jump is now. If I choose a value to the left of -3, like -4, if I plug -4 in, I end up with -1. So simplifying this, that ends up being -9/2 is our limit. Again, vertical steps would be much better here. I just don't have the room. Okay, what is this? This looks yucky too. Is it Jumpman though? Well, I see the absolute value in the denominator. So let's see. Quadratic in the numerator. Why don't we factor to see if we can find Jumpman in here? Let's see if we can factor the numerator. So is that -2 minus 6? And then factor the GCF out of the denominator. Oh, I spy Jumpman. So we could think about, and you don't have to go through all of these steps. You need to go through enough of them. Like this would need to be shown. This first part of factoring it. But x minus 2 over 2, I could write that times the limit as x approaches 6 from the right of x minus 6 over absolute value of x minus 6. So for Jumpman, that's a horizontal shift right 6. Using direct substitution for the x minus 2 over 2, so that would be 6 minus 2 over 2 times x approaching 6 from the right. If you choose a value to the right of 6, like 7, plug 7 in for the Jumpman part, you get 1. So this ends up being 2, because that would be 4 divided by 2 is 2. Oh no, there's sign involved here. What? It's okay though. Okay, so I see the absolute value. That's kind of a indicator that this is a Jumpman, or it might be. So why don't let's look at what we can do. So GCF of 3, we could factor that out. So we'll have the limit as x approaches 7 of 3 times sine of x times the absolute value of x minus 7, and then x plus 7, x minus 7 for that difference of 2, factoring that difference of 2 squares in the denominator. So I see Jumpman here, and then this other fraction. So we can think of this, because we can think of that as a product of 2 fractions, right? Like this can be rewritten as limit as x approaches 7 of 3 sine of x over x plus 7 times absolute value of x minus 7 over x minus 7. And you can rewrite that as the product of 2 limits. However, actually I'm going to do that. Notice that this is a 2-sided limit. which, knowing Jumpman and knowing what happens, this is that -7 is a horizontal shift to right 7. So the jump is at 7. So the two-sided limit we know is D and E. If you were being asked to justify, you would want to write the two-sided, show your work for the one-sided limits. So if you were being asked to justify, you would want to show the limit as x approaches 7 from the left. I'm going to rename this. I'm going to call this function f of x. Why not? So I'm defining that to be f of x, and from the left, thinking direct substitution for this other part, it would plug in the 7, so I would get 3 sine of 7 over 14 times, from the left, that would be -1. Okay, so that would end up being equal to -3 sine 7 over 14. On the FRQ, you do not need to simplify, so you could actually leave it like that. And then the limit as x approaches 7 from the right, that would be 3 sine 7 over 14, and it would be times +1, because that limit from the right would be +1. Those values do not match. They are not equal to each other. Therefore, the limit as x approaches 7, the two-sided limit is D and E. So to justify that, you should show the one-sided limits. Okay, so those are our algebraic techniques for dealing with 0 over 0, and then thinking about the new Jumpman parent function and how we deal with that. Another way that certain functions or certain limits have to be evaluated analytically is using something we call the squeeze theorem, also known in some places as the sandwich theorem, because you could think about having one function, the top function be a piece of bread, the function in the middle as being the ingredients that are in your sandwich, and then the bottom function as being the bottom piece of bread. So it's sandwiching a function between two other functions. Sometimes those functions are given, like the bread functions are given, and you're being asked to evaluate the limit of the middle function. And then sometimes they're not. Sometimes you're being asked to find the limit, and it's usually whenever you are trying to evaluate and you've tried direct substitution, it doesn't work, but you have a product of two other functions, especially if one of the functions is a trig function, like a sine or a cosine function, that indicates that it's a squeeze theorem problem. And if squeeze theorem question comes up on the AP exam, it would probably be a multiple choice question. But I'm going to show you how you would write out the justification for a squeeze theorem. So you follow these 3 steps. So squeeze theorem says if h of x is less than or equal to f of x and f of x is less than or equal to g of x for all x in the open interval containing c, except possibly at c itself, and if the limit of h of x as x approaches c is L, and the limit as x approaches c of g of x is also equal to L. So if the limits as x approaches c of the outside functions, or the top and bottom functions, are the same, that means that the limit as x approaches c of the middle function, so the function that is contained between those two, the top and the bottom function, must also be equal to L. So the way that you write out, it's 3 steps, and the first step sometimes has more steps here. But the first step would be restating the relationship, the inequality that describes the relationship between the three functions. So h of x, like for this picture, would be h of x is less than or equal to f of x, and f of x is less than or equal to g of x. That's your first step. Second step, and sometimes you have to do some extra work in this step to get to this statement. Like if you're not given this inequality. The second step is to show the outside limit. So the limit as x approaches c of h of x is equal to L, and the limit as x approaches c of g of x is equal to L. And after you've shown that, and some people will show it just like keep it in the inequality notation and show taking the limit of all three parts. I prefer to write out the limits like this of the outside functions. So that third step, then you can go, okay, well, therefore, by the squeeze theorem, the limit as x approaches c of f of x is equal to L. Okay, so the first two examples here have given the inequality, the relationship between the three functions. So you can just restate it. So if you want to be more wordy, have it flow better, you could say something like, since this inequality, second step is show the limits of the outside function. So it says x approaches -1, because we're trying to find that limit for g of x. So of -3x, so using direct substitution, that would be +3. And the limit as x approaches -1 for the upper function using direct substitution, that would be 1 minus 1 plus 3 is 3. And then those two limits are equal to each other, so we can say, therefore, by the squeeze theorem, the limit as x approaches -1 of g of x is also equal to 3. Now this may come up as a multiple choice question, but also we use squeeze theorem later in this class, so it's important to know what squeeze theorem is. We're talking about it. Okay, this is another one. So we're given the inequality. We're being asked to find the limit of that middle function as x approaches 1. Here's our justification. So natural log of x plus x squared is less than or equal to f of x. And f of x is less than or equal to e to the x minus 1. Showing the limits of the bread functions. So natural log of x plus x. So natural log of 1 would be 0 plus 1, right? Because e to the 0th power would be 1. So that just is equal to 1. And the limit as x approaches 1 of e to the x minus 1, that would be e to the 0th power, which is just 1. So we can say, therefore, by the squeeze theorem, the limit as x approaches 1 of f of x is equal to 1. Okay, so if you try direct substitution here, doesn't work, right? Because of you'd have 1 over 0, sine of 1 over 0. There's not algebra, like we can't retcon this, we can't LCM over LCM. So what we can do is start with sine of 1 over x. And we know that the range of sine is between -1 and 1, right? So sine of 1 over x is greater than or equal to -1 and less than or equal to +1. Well, now to get to this function, we can multiply each part of this inequality by x squared. So we'd have -x squared is less than or equal to x squared times sine of 1 over x, which is less than or equal to x squared. Okay, so now we're ready to take the limits of those outside functions. So the limit as x approaches 0, and I know it's 0 because this is the limit we're taking, of -x squared would be 0, and the limit as x approaches 0 of x squared would also be equal to 0. Therefore, by the squeeze theorem, the limit as x approaches 0 of x squared times sine of 1 over x is also 0. Okay, so now let's look at some limits involving trig. Now, limits that involve trig functions, you should try direct substitution first. But sometimes direct substitution does not work. So we're going to look at some where it doesn't work. Now, we're going to be using these two special trig limits, which if you check out their graphs, do I have Desmos somewhere? Where's my Desmos? Okay, so if we look at the graph of sine of x over x, we zoom in. So when x is equal to 0, it's undefined, but it does appear that the graph would be approaching +1. You can see that there. And then let's not graph that. So for y equals 1 minus cosine of x divided by x, which would also be undefined at 0. But you can see graphically the graph is approaching 0. Okay, so we're going to be using these limits. Okay, so we're going to evaluate these first three limits here, referencing the first of the special trig limits. Okay, now x over sine, that's just the reciprocal of sine of x over 1. So all of the outputs are going to be of x over sine are going to be the reciprocals of sine of x over x. And its limit will also be the reciprocal, which the reciprocal of 1 is just 1. And you could check that out graphically as well. Now, to evaluate the limit of sine of 5x over 5x as x approaches 0, remember think direct substitution first. You get 0 over 0 if we were to try direct substitution. But what's that 5 doing? That 5 is a horizontal compression, right? The graph of sine of x over x is being horizontally compressed by 5. So it's not doing anything, it's not vertically stretching or anything, but it's horizontally compressing. So that limit is still going to be equal to 1. And then for the limit in C, x divided by 2 divided by sine of x over 2, when we're dividing the x values by 2, that's horizontally stretching the graph by 2. So that limit's also going to be equal to 1. So that allows us to kind of come up with a new rule that we can memorize, a new limit, more general limit than just the limit as x approaches 0 of sine of x over x. So we can say that the limit as x approaches 0 of sine of a times x over a times x will be equal to 1. So if those coefficients match, so where there's just a horizontal stretch or compression. Now what about this one? Well, that minus 4 would be a horizontal shift to the right 4, and it's also the limit as x approaches 4. So that means that the whole graph has been shifted over to the right 4. And since we're taking the limit as x approaches 4, this will still end up being equal to 1. Okay, now, different coefficients, right? It's a coefficient of 1. We have this new rule we just came up with. Now, we are allowed to multiply by a version of 1 if we want. So if we were to multiply sine of 4x over x by 4 over 4, right, that gives us the limit as x approaches 0 of 4 sine of 4x over 4x, where the limit as x approaches 0 of that is 1. And we, by the scalar multiple rule for limits, we could pull that 4 out. So that ends up being 4 times 1, which is just 4. Okay, limit as x approaches 0 of sine of 7x over 6x. Well, the 7 and the 6 don't match. But we could multiply by a version of 1 in order to use that special trig limit. So I'm going to think about pulling the 1/6 out here. And then if I multiply by 7 over 7, well, I could actually pull the 7 in the numerator out as well, huh? Because that'll end up being 7/6 times 1, which is just 7/6. And then for this one, we could think about pulling the 3 out. Okay, so then we would want to multiply by pi over pi. So we could pull the pi out in the denominator, and we would have pi over x over sine of pi times x. Or pi x over sine of pi times x. So this would end up being 3 over pi times 1, which is just 3 over pi. So you might notice we could actually replace this rule with something different. So we could actually, because for all of, right, like this ended up being equal to a over a, which is 1. So we could actually rewrite this as a more general rule here and say the limit as x approaches 0 of sine of ax over bx is a over b. And then the same thing is true for the reciprocal, right? Okay, and then let's look at this one. Now notice, we always should be thinking direct substitution, because that'll get you, if you're just always looking for some sort of like trick and you don't remember direct substitution, you might get real stuck. Now if we use if we use direct substitution here, because this isn't x approaching 0, notice what happens. We get 3 over sine of pi, which is 0. This isn't 0 over 0. We ran into this above in that discuss problem. So we have a number over 0. That means that there's actually a vertical asymptote. And again, this will be talked more about in section 1.5. But that means there's a vertical asymptote at x equals to 1. So all we would be able to say is d and e. You could think one-sided limits, see if you could say positive or negative infinity for y it's d and e, but we'll just say d and e. Okay, so now let's reference that second special limit, which was that as x approaches 0, 1 minus cosine over x is 0. Now the reciprocal of that is going to be d and e. Okay, and you could check that out graphically, but there's, yeah, it would be d and e. And that part of that is the reciprocal of 0 is infinity, but I want to give you a more formal proof for that I don't have handy right now. Okay, the limit as x approaches 0 of cosine of x minus 1 over x, well, that's just applying a vertical reflection to that special limit. That vertical reflection doesn't do anything, so this limit is also equal to 0. Multiplying x by pi, well, that's a horizontal compression. That's not changing what the graph is approaching, so it'll actually be 0 as well. And then the plus 7 is a horizontal shift to the left 7, and then we're also taking the limit as x approaches negative 7. So all of that's being shifted over, limit will still be 0. This is a little bit more complicated, but let's see what's happening, because it looks similar. It looks like we could be referencing that special trig limit. So notice that the numerator has a GCF of 4. So if we factor that out, we'll have 1 minus cosine of 11x. And then we can have 4 cancel with a 4 in the denominator, leaving us with 11. So that'll be the limit as x approaches 0 of 1 minus cosine of 11x over 11x. So that 11 is a horizontal compression. So this will just be 0 as well, referencing that special trig limit. Here's an example of using some algebra and special trig limits. So there's not any of the other, no LCM or LCM, no retcon. You can't just right away go, oh, that's 1. That doesn't work. So what you could do, though, is split this up into a sum of 2 fractions. So this would be the limit as x approaches 0 of x over x plus sine over x, or sine of x over x. And then you could use the addition property of limits and go, okay, well, limit as x approaches 0 of x over x, which simplifies to be 1, plus the limit as x approaches 0 of sine of x over x. Well, that's 1, right? The limit of the constant would be 1 plus that special limit is 1. So this limit ends up being equal to 2. And then sometimes we'll have to use trig identities. Woohoo! Okay. Now, sine and cosine were our special trig limits. It can be helpful to kind of do our fallback from when we were verifying trig identities. Change everything to be in terms of sine and cosine. So if you try direct substitution first, you end up with 0 over 0. So I'm going to rewrite tangent as sine over cosine since it's in the denominator. This could also be written as cosine of x over sine of x, right? The reciprocal of what tangent's equal to, times x. And then I can rewrite that product as cosine of x times x over sine of x. Which then, if we think about using the multiplication property of limits, the limit as x approaches 0 of cosine of x times the limit as x approaches 0 of x over sine of x. Cosine of 0 is 1, and then the limit as x approaches 0 of x over sine of x is 1 as well, so that limit's just 1. Okay, a little bit more complicated. Well, I do see sine in the numerator, x in the denominator. So let me rewrite this as 4 over cosine of 2x times sine of 5x over x. And then if I multiply by 5 over 5, I can rewrite this as limit as x approaches 0 of 20 over cosine of 2x times the limit as x approaches 0 of sine of 5x over 5x. So direct substitution for that first limit would be 20, and then times 1, so this is 20. Okay, one more. So tangent in there, I'm going to rewrite tangent in terms of sine and cosine. So I'll have the limit as x approaches 0 of sine of 3x over cosine of 3x times 1 over sine of 4x. So those signs can't cancel. It would be nice to be able to use that first special limit, but I need an x in the denominator for this sign and an x in the numerator for this sign. So why don't I multiply by x over x? So then I'll have the limit as x approaches 0 of, I'm going to have the 1 over cosine of 3x here. And then I'll have sine of 3x over x times x over sine of 4x. So I could write this out again, taking the limit of each factor, but let's see. If we use direct substitution for this first limit, that would just be 1. And then using that rule for the limit here, we get 3. Right? Sine of bx over ax would be b over a, or sine of ax over bx would be a over b. So that would be 3. And then the limit of x as x approaches 0 of x over sine of 4x would be 1/4. So that's 3/4. Okay, and you could always confirm these graphically. If you're on an assignment, you want to double check this, you could always graph it on Desmos, your graphing calculator, to double check. And that's it.